Kinetics involves studying the speed at which reactions take place, which is called the reaction rate. Studying reaction rate is what chemical kinetics is. When we can use kinetics actually to kind of determine what's happening within a reaction. That's called a mechanism, which is a step-by-step view of the reaction. You can see here in this image the reaction. We have A plus B goes to C and X plus Y goes to Z. Reactions that have a fast rate are going to turn into products much quicker than reactions with a slow rate. It takes them a lot longer. You don't have as much products in the same amount of time. Factors that are going to affect reaction rate are the state that the reactants are in, the concentration, the temperature, and whether there's catalyst or not. Starting with physical states, we know that the more likely reactants are to collide, then the more rapidly they react. So this is called collision theory. Homogeneous reactions tend to be faster when all of the reactions are in the same state. Heterogeneous reactions are slower. These can be sped up when we have a high surface area. So when we're dealing with molecules that are like in a powder form, they're going to react faster than if you were all combined into like a chunk. Increasing the reaction concentration generally increases the reaction rate because there are more molecules, more reactants available, so there's more collisions that are likely to happen. In this image we see oxygen in the air is about 20%, so when we burn still wool, which is iron, to get iron oxide, this happens a lot slower than when we have a flask that's purged with just pure oxygen. That happens a lot faster. Temperature also increases the reaction rate. That has to do with the kinetic energy of the molecules increasing. It gives us a higher, when we have a higher temperature, molecules are generally moving faster, so their kinetic energy is faster. So when they're moving faster, they're likely to collide more often, and the energy with which they collide also is higher, so they're more likely to overcome the activation energy, which we'll talk about later. Catalysts affect the rate without being involved in the overall equation. So they kind of help the collisions by making it either more possible or by providing another alternative path for a reaction to happen. And they're really important in many biological processes. So getting into the actual math, rate is a change in concentration over a given time. So we have change in concentration, that's usually in molarity, divided by the change in time, often in seconds, but it doesn't matter. Types of rate that are measured are either average rate, where we're just taking the difference between two different points, instantaneous rate, which will use a tangent line of a slope, or the initial rate, which is instantaneous rate at time 0. So here we could say, okay, like if I wanted to know the average rate, I would use those 2 points, and that slope would tell me the average rate between those lines. If I want to know the instantaneous rate, though, I'm just going to take, I'm going to approximate a tangent to the slope at that given point, and then use some data from the graph to approximate the slope. So here we have a reaction where we have A is going to B. Initially we have all of A, then at 20 seconds we have 0.54 moles of A and 0.46 moles of B. Notice these add up to 1 mole total. It's due to conservation. And then at time 40 it drops down to 0.3 and up to 0.7. So if we want to know the average rate for which A disappears over time, we're going to do the rate is the change in concentration of A over the change in time. And if I want to know disappearance, it's going to be a negative because it's the rate that it disappears. So we'll do 40 seconds, final minus initial, so 40 minus 20 seconds. And then at 40 seconds, we have 0.3 moles of A, and then minus 0.54 moles. So we know that A went down by 1.2 times 10 to the negative 2 molar per second. Or it should actually be moles. So if the experiment runs for 60 seconds and we only have 0.16 moles of A, then we can do 1 minus that, so that would be 0.84 moles of B. So which of the following statements are true? So at 60 seconds there are 0.84 moles of B? Yes. The decrease in number of moles from A from T0 to T20 is greater than from T40 to T60, so we can calculate. From 0 to 20 we know we dropped 0.54, so we went down 0.54 minus 1 over 20 seconds, which gives us at this first 20 seconds went down by 0.0023 molar per second. If we want to do from 40 to 60 seconds, we'll do, this is a 20-second interval, so we'll say that it went down from 0.16 minus 0.3, so we get 0.4 divided by 20, 0.007, so this is also true, and that is a greater change at beginning than at the end, which is pretty common. So when we're looking at reactions, we could either be measuring the rate that the reactants disappear or the rate that the products appear. So if we're dealing with a reactant, like we do here, then that's going to be disappearing. So we're going to put a negative sign out front. Rate should always be positive because we're just generally talking about a reaction, the rate of the total reaction, which is going to be a positive number, a positive change over time. So if we're monitoring reactants disappearing, then we want to put a negative sign out front. So when we plot this data, we're going to find out more info about the rate. Slope at any one point is the instantaneous rate. And when we do this at time 0, this is the initial rate. And that's what is most important to chemists, because that's the fastest rate that's happening, so that will give you the maximum amount of speed that the reaction is going to have. So what you would end up doing is measuring, time is going to be your independent variable, and x will be your concentration will be your dependent variable that you're measuring. So you're starting with your initial concentration, and if you plot this, you get this slope. But you can see that it's not a linear curve. It's happening. There's a slant in the curve, so we're not going to be able to just use like the slope of a line over the whole thing. So if you just took the difference between 2 points, you can get the average rate between those time periods. But the better thing to do to get an exact rate at a certain point is to take the tangent line. Note that many reactions typically slow down over time, so it's a nice thing to be keeping track at all different times. So let's just approximate what the slope is at time equals 600. So they have this line for us, so let's use 2 points. You can use any points on this blue line because that's where the tangent line was drawn. So if we just use the point here and point here, do whatever you need to do to make it easy for yourself. We could find the rate at 600 is the change in concentration. So let's do 800 seconds minus 400 seconds. And so the concentration at 800 is about 0.18 molar, and then the point at 400 is about 0.042. So when we do that math, we get 6.0 times 10 to the negative 5th molar per second is our rate. Doing the same thing here at time 0, they have this nice little tangent line for us, so we could use anything on that slope of the line. So let's find the rate. Let's use points 210 here, which is where it exactly hit the 0.06 mark on concentration, and 0. So we'll say 0.060 minus 0.1 molar over 210 minus 0 seconds. And what we get is 1.9 times 10 to the negative 4 molar per second. Now, if you didn't get exactly that, maybe you use this point up here, or you found a different point that you like, that's fine. It should be pretty close though. If we do it for something at 300, well, then we're going to want to draw a tangent line. I'll just try my best on here with a tablet. It's tricky, but what I recommend, is to use a book and a pencil, paper and a pencil to help you. So let's use that point and that point, sure. So we could do rate equals, so for 300, we'll do, so let's just do, well, the way I did it on a piece of paper is I took the points at 600 seconds and 300 seconds, since I know that exact point. So we'll do negative 0.020 molar minus 0.055 molar, and those are the points at 600 seconds and 300 seconds. So when you do that, you get 1.2 times 10 to the negative 4, so we can see that it did indeed slow down. So which of the following could be the instantaneous at 1000, so it should be less than all of these, and our 600 point, which was 6 times 10 to the negative 5. So that's the same as at 300. This is bigger than at 600. This is bigger than at 600. So the only possible one is D. So like we said earlier, rate can be determined using reactant or product, but will it give us the same rate? Well, we did see earlier that a reactant is being formed, so we'll see that concentration change increase while products are going to decrease. So those are going to give us opposite signs. It also is going to depend on stoichiometry. If you have something that appears faster, then its rate's going to appear faster, so we want to take into account. So using the example we did earlier, the rate for the reaction, we do negative change in concentration for our chlorine compound over time, but if we're going to use the product, we would do a positive change in that compound over the same time. So they're going to have opposite signs, since one is decreasing, the other one would be increasing. But overall, you want your total rate to be a positive number. If the equation is not 1 to 1, then we're going to need to use the stoichiometry of the reactants and the products in there. So our rate's going to be equal to negative 1 over the stoichiometric coefficient of each compound times the change in concentration of that compound. Now this factor here, that's what we measured on the graph. So if I want to know the total rate, I'm going to find that number, calculate it from the graph, and then do negative 1 over A to get the total rate for the reaction. Same thing with B. When I have a product such as C or D, I'll keep the positive and then times by the 1 over the coefficient over the concentration change over time. So if I have this reaction here, then I would know that the rate of the reaction is going to be equal to negative 1 over 2, since it's a reactant, times the change in concentration of ozone over change in time, and that's going to be equal to positive 1 over 3 times the change in concentration of oxygen over time. So those are how those two are related. Now it says, if I'm measuring oxygen and it's appearing at a rate of 6 times 10 to the negative 5 molar per second at any instant, what's the rate that ozone is disappearing? So basically on a graph, I see that this is 6.0 times 10 to the negative 5. So how can I find this? Well, what I'm going to do is I'm going to say negative. I need to basically solve for negative 1 over, negative change in ozone over time. So I'm going to multiply both sides by 2 to cancel out that 2 and to get this part by itself. So what I get is a negative change in ozone over time equals 2/3 change in oxygen over time. And since this number is 6 times 10 to the negative 5, I'll multiply that by 2/3, and what I get is 4.0 times 10 to the negative 5th molar per second. So, and that makes sense because ozone, if we look at the stoichiometric coefficient, it is disappearing. Like 2 of those disappear for every 3 oxygens appearing. So it makes sense that the rate for ozone would look slower than oxygen because it's disappearing slower because of the coefficients. How do we actually measure rates? So a few different ways, and these aren't all of them, but one could be using the total pressure. So we can monitor the pressure and then use reaction information to calculate the partial pressure of each of the gases. We could use spectrophotometry, which is right here, where we're measuring the absorbance of light of any wavelength. So we've determined, what color is our reactant or a product that we want to measure and see how that absorbance changes over time. That one's a really fun and a pretty cool way to track it. Aliquots is basically taking a small sample at different times during the reaction and then testing them ex situ, so out of the reaction. And then gas chromatography can measure different concentrations of gases for each component in the mixture. So how do we kind of determine how each reactant kind of affects the overall reaction? Well, what we want to do is, if we have 2 reactants, we want to try adjusting the concentration of one of them while holding the other one constant. So for this reaction here, numbers 1 through 3, we're going to adjust ammonium but keep nitrite the same. So in that case, we're seeing how ammonium is impacting the rate. For number 4 through 6, we're keeping ammonium the same and changing nitrate. So any kind of changes to the rate will be due to nitrate's concentration. And then we'll take ratios of the 2 to see the impact. So for 1 through 3, we'll holding nitrate constant, so we'll check out ammonium. So we'll take the rate of 2 of them, the ratio of the rates. So we'll say that, so if we take the rate of the second one, 10.8 times 10 to the negative 7 divided by 5.4 times 10 to the negative 7 equals our concentrations, so 0.02 over 0.01, and we see that for every 2, the ratio of the rates is 2, and then the ratio of the concentrations is 2. So these are equal to each other. So what we actually do is say, like, okay, how did changing the concentration impact it? So raise it to the x. So what does x need to be for this reaction, for this equation to be true? Well, x is equal 1. So this is a first order reaction with respect to ammonium. We'll do the same thing for nitrite using experiments 4. So if we use 4 and 5 as our 2, and it doesn't matter which 2 you use, then we'll do the rates. So 21.6 times 10 to the negative 7 over 10.8 times 10 to the negative 7 equals, now our concentrations of those two, 0.0404 divided by 0.0202. Now this is to the y. So we see the ratio of the rates is 2, and the ratio of the concentrations is 2 to the y. So y must equal 1 for this reaction to be true. So what we'll say is, what we get is the rate law, which says that the rate is equal to, for this case, the concentration of ammonium to the 1 times the concentration of nitrite to the 1. And normally when something's raised to the 1, we don't include it, but I will just for the purposes. So one way we can do the rate, calculate the rate, is using the change in concentration over time if we do a long reaction. But if we just check out the instantaneous rates at different concentrations, we can also find out that the rate equals the concentration of A, one of our reactants, raised to, not the coefficient A, but X, times by B raised to the Y. So these are the reaction orders with respect to each reactant. So the order for each of those reactants was 1. The reaction, though, is second order overall, because so we basically just add the exponents to get that. So these are not determined with stoichiometry, they are determined experimentally. And I forgot, dang it, the K value. K goes up front. This is the reaction rate constant, and it is a temperature-dependent quantity that helps us to kind of normalize our reaction rate. And we'll be gathering it with reaction rate experimental data. So, like I said, the order of the reaction must be determined experimentally. This is very important. So when we have this reaction here, 2 dinitrogen pentaoxides decompose, we get the rate determined experimentally is only first order, even though the coefficient was 2. That's because experimentally that's what they determined. Here, hydrogen and iodine react, and they're both first order. That's just coincidence. Here we have this trichloromethane and chlorine reacting, first order with respect to trimethylchlorine, and half order with respect to chlorine gas. So kind of weird, but it happens. We're not going to focus on those half orders, but just a fact that they can do it. So reactions that have a rate constant of 10 to the 9th or higher, those are considered fast, and 10 to the 9th or lower are considered slow. And honestly, I haven't really been thinking about those too much, but it's good to know. So if we have this reaction here, they determined experimentally this was a rate law. We're going to rank their mixtures in order of increasing rate. So for number 1, the rate is equal to K times A. Now A are the red, so we're going to do 5. We're plugging in here, times blue, 5 squared. So we get the rate is 125K. For 2, we have the rate equals K times, we have 7 reds and 3 blues squared, so that gives us 63K. For the third one, it's flipped, so we have 3 reds and then 7 blues, which gives us 147K. So we could say that 3 is the fastest, then 1, and then 2. So if we were to do the same thing, but if we had a different rate law where it's second order with A and first order with B, we plug in again. I'm going to let you guys do this. I will let you know that it is E, where it kind of flips around, where 3 is now the slowest, 1 is in the middle, and 2 is the fastest. And then when the rate law is just first order with both, we get that number 2 and 3 are the same, and then the fastest one is 1. In these set of problems, they want to look at the total order and also units. So the overall reaction orders for 14.9 and 14.11. So 14.9, we have just first order overall. It should be first. For number 1411, we have 1 plus a half, so the overall order is 1.5 overall. The units for the rate law, so units for rate, so basically what we have to do is the rate, here let me actually fix it. We have rate equals K times the concentration to the first power. So rate units are molar per second. We are going to solve for the K, and then concentration is just molar into the first. So we're going to get K by itself, divide by molar. So the units of K are, the molar cancels out, we just get inverse seconds. We can do 1 over S or S to the negative 1. For this next one, we're going to still have rate, molar per second, K, and then the overall order was to the 1/2. So we could do 1.5 or 3/2. Let's do 1.5. So we're going to divide by molar to the 1.5 on both sides. Okay, so that cancels out. So the K constant, so when we have exponents, we have 1 on the top, and when we divide, we are going to subtract the exponents. So we get molar to the -1/2 times second to the 1/2. And so that gives us A. For reaction in 14.10, it wants to know the order with respect to hydrogen. Well, there's just a 1 there, so just first order. And the units for this one, we have second order overall, so we can do molar per second equals K times molar squared, because of our concentrations are squared, divide by molar squared, divide by molar squared. So we have 1 minus 2, so we end up getting m to the -1, s to the -1. So for second order reactions, this is the units of our rate constant. For first order reactions, this is the units of our rate constant. We don't see those weird half ones. In this reaction, we want to determine what's the rate law and then what's the rate constant. So generally we have the rate equals the rate constant times nitrogen dioxide to the x, carbon monoxide to the y. So we want to find out what x and y are. So what we want to do is compare two experiments. It doesn't matter which one you want to go first, but we want to find ones where, let's just do nitrogen dioxide. So we want to find ones where carbon monoxide are the same, so that way they cancel out. So I'll show you. We're going to do rate of the second one over rate of the first one. And that's going to give us K times nitrogen dioxide to the x over carbon monoxide. And actually I'm going to plug in those values so we can see it. So nitrogen dioxide is 0.1. Nope, we're doing it for the second one. 0.2 molar to the x, and then 0.1 molar to the y for carbon monoxide. Then we're going to do rate 1, so we'll do K again, times 0.1 for nitrogen dioxide to the x, over again 0.1 for carbon monoxide to the y. Since we use those two, we have to use those values. And that whole thing equals 0.0082 divided by 0.0021. So notice our k's cancel out, and 0.1 to the y over 0.1 to the y cancels out. So that's why we could do that. So we get here about the ratio of the concentrations, about 2 to the x equals, this is about 4. So x in this case needs to equal 2 to make 2 to the x equal 4. So we'll say it's at second order with respect to nitrogen dioxide. So we'll put a 2 there. And now we'll find for carbon monoxide. So here for carbon monoxide, we want to find two experiments where nitrogen dioxide stays the same. So we'll do 2 and 3. So rate of 3 over rate of 2 equals the 0.0083 over 0.0082 equals, and I'm not going to draw this out again, we know that they're going to cancel. So we'll just do the concentrations of carbon monoxide, so 0.2 to the y over 0.1 to the y. So these are, the ratio of the rates is 1, basically 1, divided by 2 to the y. So anything, to get any exponent raised to that power to equal 1, it needs to be 0. So y equals 0. So what we get for our ending rate law is rate equals K times nitrogen dioxide to the second, and carbon monoxide to the 0, which is just 1. So now in order to find K, the rate constant, we just need to plug in our rate law. Any experiment will do to get that. Let me use a different color. So we'll do, let's just do the first one. So we have our rate, which is 0.0021 equals k, and our rate is, you really do, I need to do this, write the units, because we're going to need to cancel out. Molar per second times k times the concentration of NO 2.1 molar squared. So we're going to divide that over, and what we get is our K is equal to 0.21 inverse molar inverse second. This is going to be a very similar one where we have the rate of two components of A, so rate law times rate constant times K, A to the X and B to the Y. When we have two components, all we need is a minimum of 3 experiments in order to do this. 2 holding A constant and 2 holding B constant, so we can find those out. So they want us to find the rate law, the rate constant, and the rate of the reaction when we have those concentrations for A and B. So for A, we're going to, doesn't matter what you do first, let's just find B. So we're going to hold A constant. So we'll do the two rates are we're going to do for experiment 2, so 1 and 2. So 4.0 times 10 to the negative 5 divided by 4.0 times 10 to the negative 5. So we're already seeing there's not a huge change. And then we're going to do for B, it'll be 0.2 to the y over 0.1 to the y. And so we get 1 equals 2 to the y. So again, in this case, y is 0. So 0 order with respect to b. So let's put a 0. 0. Okay. Then for x, we need to do the same thing. So now we're going to hold b constant. So do 3 and 1. So we have, for b, 16 times 10 to the negative 5 over 4 times 10 to the negative 5 equals 0.2 times x over 0.1 times x, and that gives us 4 equals 2 to the x, and I promise it won't always be this nice. So here we have x equals 2. So our rate law is rate equals k times a to the second. So to find the rate constant, we'll find one. Let's pick, again, just one, sure, why not? 4 times 10 to the negative 5th molar per second equals k times 0.1 molar squared. So we divide that over, and we get k equals 4 times 10 to the negative 3rd inverse molar inverse second. So the next step, taking it a step further, is finding the rate when these are the case. So we'll plug in our rate law. Rate equals k, which is 4 times 10 to the negative 3rd inverse molar inverse second, times our concentration of A, 0.050 molar squared, times B to 0, which is just 1. And what we get is 1.0 times 10 to the negative 5th molar per second. Now we're going to work on each type of order of reaction and a little bit about each one. We're going to start with first order reactions. So with first order reactions, for the total rate, it only depends on one of the reactants to the first power. So it has the rate law, that is rate equals k times a reactant to the first power. So if we relate both definitions of rate, that rate equals k times a, as well as rate equals negative change in a over change in time. If we set those equal to each other, since rates are going to be the same, we get k of times a equals negative change in a over change in time. So what we're going to do is rearrange so that all of the components, all of A are on one side, and then everything else is on the other side. So what that ends up we're going to move this guy over, divide, and move the delta t, negative delta t over. So we get delta change in A over concentration of A equals negative k delta t. So if you've taken calculus, this should look kind of familiar to something of like of a derivative. So instead of a delta, we'd have a d, so dA over A or dx over x. So what we want to do to get rid of the delta is we're going to integrate both sides from 0 to A and from 0 to t. So what we end up getting is, when we integrate, something that looks like dx over x, that gives us natural log of x from your initial to your final point. So what we get is natural log of A, concentration of A, over A naught. I'm not going to put concentration just for the sake of writing. And that's going to be equal to negative kt. So we can rearrange this to get rid of a division within a natural log. That's the same thing as a subtraction. If you'd like me to show you this like in person, I'd be happy to walk you through it. But what we end up getting is ln of the concentration of A equals negative kt plus ln of your initial concentration of A. So what this kind of looks like is y equals mx plus b. So basically what happens is when you take all of your concentrations and your times, and you just plot the natural log of all of your concentrations that you've been monitoring versus time, the slope of that will be negative the rate constant, and your intercept will be the natural log of your initial concentration. So a plot of natural log of the concentration of your reactant versus time is linear, and the slope will equal negative k. This could be really helpful because if you just have one plot and you are able to plot this and it becomes linear, then you know that your reaction is first order and you don't actually have to adjust for various concentrations. You could just do it one concentration over a long period of time. So when we look at this conversion of methyl isonitrile to acetonitrile, this is a first order reaction. If I was to just plot the pressure, which is proportional to the concentration versus time, it doesn't look very linear. But if I took the natural log of all of these values and plotted those versus time, we get a line. And that line, since that's linear, it tells us that this is a first order reaction. And then if I was to take the slope of this, and we're going to get very familiar with Excel or Google Sheets so you can find the slope, then your slope, which is m, is going to be equal to negative k. So we can find the rate constant. For half-lives of a first order reaction, half-life in general is the time it takes for half of your reactant to be used up. So for a first order reaction, our integrated rate law is natural log of A equals negative kt plus the initial concentration of A. So to find the half-life, we want to know when the time it's going to take for our concentration to be half of what we started with. So what we could do is take ln of A naught over 2 equals negative k times the half-life, we'll just call it t1 half, plus ln of A naught. So then we can move this whole thing over, boop, and we get ln of A naught over 2 minus ln of A naught equals negative k t1 half. I'm getting real funky with my k's. I don't know why I'm doing like cursive k's, but just bear with me. So natural log of ln of A. So basically what we can do is recombine this, and when we do that, the natural log goes on the bottom since we're subtracting. So we get ln of A naught over 2 A naught. This one came from that guy. So the A naughts are going to cancel out, and that equals negative K T1 half. So when we solve for T1 half, then we can divide this whole thing by negative K. And so we get that the half-life for a first order reaction is equal to the natural log of 2. Okay, so before I finish that up. So we have the natural log of 1 over 2. I could flip this and make it, but put out a negative. So then the negatives cancel out. But the 2 will come up top. So I get natural log of 2 over K. I know, weird. But the natural log of 2, I think this is the easiest way to remember. The book also says the natural log of 2 is 0.693, but I think it's just as easy to write, to press in your calculator natural log 2, enter, than it is to write 0.639, and it's a little easier to remember. So that is our half-life. Notice it does not depend on how much you start with, it depends on your rate constant. So let's do an example. We have dimethyl ether is a first order process, so it tells us that. That's a good sign. And it has a rate constant of 6.8 times 10 to the negative 4th. So here's our reaction. If the initial pressure is 135 torr, what's the pressure after 1420 seconds? So for this problem, oh, dang it, we already have it written up. Damn it. Okay, it's fine. What we want to do is take our integrated rate law, natural log of our initial concentration, or of our concentration equals negative KT plus our natural log of our initial concentration. So we're trying to find the pressure after a certain amount of time. So I'm trying to find out what this is, concentration. So we're going to plug in K, we're going to plug in T, and plug in our initial concentration. When we do that, we get the natural log of that, of our time, is 3.94. But we want to get rid of our natural log, so we could raise it to the e to that number. That's how we get rid of a natural log. So when we have a natural log of x, and we want to get x by itself, we could take e to that number, will give us x. So just FYI. So we see something that's less, which makes sense. We should have a smaller number. Here's another problem. Lots of words. Don't get overwhelmed or concerned by it. It says the decomposition of a certain insecticide in water at 12 Celsius follows first order, so that's something to underline, with a rate constant, so we know K equals 1.45 years. Inverse years. A quantity of this insecticide is washed into the lake on June 1st, and our initial concentration is 5 times 10 to the negative 7 grams per centimeter cubed. So that's our initial A. Okay, and then the temperature is constant, so that's good to know for the rate constant, doesn't change. So what's the concentration of the insecticide on June 1st the following year? So it wants to know the concentration. So that's basically, we're going to do ln of our component is negative K, so 1.45 inverse years, times our time. Now this is the following year, so it's just been 1 year, plus ln of our initial concentration, which is 5.0 times 10 to the negative 7 gram per centimeter cubed. So when we plug all of that into our calculator, we get that the natural log of our insecticide, we'll just call it A, is negative 15.96. So in order to get rid of our natural log, I'm going to E both sides. And so I get my amount of insecticide ends up being 1.2 times 10 to the negative 7 grams per centimeter cubed. Great. So for B, it wants to know how long will it take for the insecticide concentration to decrease to 3 times 10 to the negative 7? So we want it to, from its initial concentration to get down there. So now we're trying to find a time. So again, we're going to plug in, but now we want to know, okay, when will it be at 3.0 times 10 to the negative 7? And we're going to again do negative k for 5 inverse years. And now we're trying to find the time, plus ln of 5.0 times 10 to the negative 7 gram per centimeter cubed. So we're going to move this whole thing over by subtracting. And then, so we'll subtract that over. And then, let's put a naught. And then we're going to divide that whole thing by negative 1.45. And we should get our time that it takes is 0.35 years. Okay, which makes sense because it's a full year away is, we're down to 1.2 times 10 to the negative 7. We don't want to get quite there, so it should be under a year. For C, it wants to know the half-life of the decomposition, so we're just going to plug into the half-life of a first-order reaction. So T half-life equals ln of 2 over k, so 1.45 inverse years. So that gives us 0.478 years. So just doing a logic check. After 1 full year, we dropped down to about a quarter. So it would make sense that after a half year, we would be at the half-life. And then for D, I'm going to do a different color just because it's kind of hard to follow now. How long does it take for the concentration to reach a quarter of the initial value? So for this one, we want to realize, okay, it's going to take to get, so if we start with 1, I'm just going to do a little graph. If I start with 1, after 1 half-life, I'm going to get to half. After 2 half-lives, I'm going to reach to a quarter. So how long does it take for it to get to 1/4 of what it initially was? Well, that should be 2 half-lives. So if you calculated the first half-life, then to get to a quarter, then that would be 2 half-lives. So we could do just 2 times what we found earlier, and that will give us 0.9559 years. And another cool thing I've just learned over the time I've been teaching is that if you want to find out, we did ln of 2 because that was the half-life. If you want to find out a quarter life, you could do ln of 4, an eighth of a life, ln of 8. So you can follow the fractions down that way too. That'll work, but try it out. Don't test it before you just use it. So for this reaction, we're going to go back to one of the experiments we did earlier, and we want to just use a graph to approximate the half-life. So when we look at the half-life here, we start with 1. So using the graph, we want to go to where it was half. So the concentration at half is 0.05. We're going to go over until we get to hit the curve, and then we're going to go down. So sorry, that was a little hard to do. So the half-life from here, just by looking at the graph, is about 350 seconds. Depending on your skills and ability to extrapolate, you might get something a little better. And then B, use the half-life to calculate the rate constant. So we know that the half-life for a first-order reaction is ln of 2 over k. So if we know the half-life, then we could do 350 seconds equals ln of 2 over k. We're going to solve for k now. So what you could do is flip those two. So we get the rate constant equals ln of 2 over the half-life, 350. And we get about 2.04 times 10 to the negative third inverse seconds. I'm doing that as if this is 340. That's what the textbook is using, but if I use 350, I should get something similar. So for second order reactions, we're only going to specifically focus on the rate when only one of the components is raised to the second order. So that's where we have rate equals k times a to the second power. So when we do that, we're again going to set our rate law equal to, we're going to use that and our original rate relationship, which is the negative change in a over the change in time. So when we set those equal to each other, we get negative change in a over change in time equals k times a squared. Again, we're going to set all the things equal to, or all of the a's on one side, all of the everything else on the other side. So we get change in a over a equals negative k delta t. Integrate, oops, and that should be squared. Now when we integrate something that's like dx over x squared, it becomes negative, this ends up being negative 1 over x raised to, wherever you're integrating from and to. So ultimately when we integrate and rearrange, we get 1 over our concentration of A equals KT plus 1 over A naught. So once again, we have Y equals mx plus B. So when we, again, just take our concentrations and do the inverse of them, so you would just hit 1 over those and plot that versus T, our slope is now related to K. And so we'll see that. And then our intercept, we could take whatever our intercept is and inverse it to get A. So when we look at an example of nitrogen dioxide decomposing, this happens to follow second order reaction. So if we plot, if we plot just the concentration of nitrogen dioxide versus time, we would get something that looks like that. And then, so that doesn't look linear. Then we could also plot the natural log of the concentration over time. If it was first order, it'd be linear, but notice it's not. Now if we plot 1 over that concentration versus time, we do get something linear. So it is linear for 1 over nitrogen dioxide concentration, but not for natural log of nitrogen dioxide, which means it's second order. So again, if we just take some data, we run our experiment for like 5 minutes, all we have to do is take our data points, and quickly in Excel, it's really quick. You just drag and drop your natural log and your inverse of your y values and then plot them. You can just take a quick glance to see how linear they are. And in this case, our slope here, we can just find the trend line, is equal to k. And our intercept is equal to 1 over our initial concentration, which theoretically we should know, but just fun fact. So let's do this practice problem. I'm actually going to save this one for in class because we're going to need a computer. So we'll come back to it, but I'm going to encourage you to, in your computers, take your time, take these data points, and then plot them. On this next column right here, just do equals natural log of whatever this value is. Click on it, hit enter, and then in the column next to it, do equals 1 divided by the concentration, hit enter, and then you can drag those columns down so you can plot it. Then you'll plot time versus concentration, time versus natural log of concentration, and time versus inverse of concentration. and you'll be able to determine what order it is. And then we'll pick this up in class. For the second order, to get the half-life, we're going to do the same thing. We're going to take our rate law, and we're going to find the time where our concentration has reached half of where we started. So what we get is 1 over our initial concentration divided by 2 equals 1 over our initial concentration, plus KT, and KT 1/2. What happens here is the 2 is going to flip up, and then we're going to move this one over here by subtracting. So we get 2 over A naught minus 1 over A naught equals K times half-life. So 2 over A naught minus 1 over A naught is just A naught, or 1 over A naught, equals K times T 1/2. So we could divide by K, and we get the half-life of a second order reaction is equal to 1 over K times your initial concentration. So notice it does depend on what you start with, what your half-life is going to be. Where in first order, it didn't actually matter with how much we started with. We reached our half-life only depending on the rate constant. For zero order reactions, this is a case where the rate is independent of our concentration of any reactant, and that's where rate is basically just equal to the rate constant. So notice for a zero order reaction, it just goes down. There's no relationship other than linear. So that's what a zero order reaction is. These are linear with concentration, so we don't have to do any kind of rate law. We could just look at the graph and say, the rate or the concentration at any time is equal to negative times the rate constant times time plus your initial concentration. So it literally just does follow a y equals mx plus b because it is a line already. If we solve this for half-life again, so find the time where this is half of what we started at, we get half-life equals your initial concentration divided by 2K. And I encourage you to try to work that out on your own with some of the algebra that goes along with it. And if you want me to help you with it, just ask. Here's a nice little summary of all the rate laws and some of just the half-life expressions, as well as when they're going to be a straight line, their integrated rate laws, their units of their constant. Try not to memorize this. I would encourage you to be able to solve it, right? Just like we've done for the constants. I would probably just know, you don't have to memorize, but just know that first order is linear with natural log, second order is linear with inverse relationship, and zero order is just linear on its own. Be able to recognize what the slopes give you of the lines and the half-life equations that go with them. Notice the half-life equation for first order involves natural log, for second order involves an inverse relationship, and first order involves a direct relationship. So I'm hoping that will help keep it straight.